Okay, so going back to what I was saying. So, as I said before, Bohr's focus was on the hydrogen atom. So he came up with a model known as the Bohr model. In some textbooks, they call it the planetary model, and you're going to see why. So basically, according to the Bohr model, this is how the atom is structured as far as the electron is concerned. You have the nucleus in the middle, and then surrounding the nucleus, we have what are called orbits within which the electrons will travel, all right? And this is the reason why they call this in some textbooks the planetary model, because this is basically, of course, what we know about the arrangement of the planets around the sun. You have the sun in the middle, and you have the different planets surrounding the sun traveling in orbit. So Bohr was suggesting that something is similar in terms of the arrangement when it comes to the hydrogen atom. You have the orbits within which the electrons will travel, and each orbit represents a separate energy level. So we have what is called the n=1 orbit, which is the one that's closest to the nucleus, and then you have n=2, n=3, and so on, further away from the nucleus, right? And what you'll find, according to the Bohr model, is that the energy increases as you go from the orbit closest to the nucleus to the ones further away. So he did his calculations and theoretical work, and he came up with this equation right here to show or to calculate the energy of each orbit. En is equal to minus RH divided by n squared, where n is the number associated with the orbit. So n=1 would be for the first orbit, n=2 would be for the second orbit, and so on. RH is a constant known as the Rydberg constant, and this is the value here. And I'm going to say more about the Rydberg constant shortly, but this is one way of expressing the Rydberg constant, 2.179 times 10 to the minus 18 joules, all right? So this is the formula that Niels Bohr came up with to calculate the energy of each orbit, right? Please note there's a negative sign here, right? And the reason why the negative sign is a part of this equation is because the negative sign indicates that there's an attractive force that exists between the electrons traveling in orbit and the nucleus, which of course is positively charged, all right? So based on this equation, if you imagine where the electron is infinitely far away from the nucleus, in that case, if you look at this equation here, that means that n, let me write this down here. That would mean that n here, if n is equal to infinity, right, which means that the electron is way out there compared to the nucleus, then that means that E infinity will be equal to 0. All right? Well, not equal to, what am I saying? No, wait a minute. Yes, E will be equal to 0. All right? So basically what that is saying is that there's no attraction that exists between the electron when it's far away compared to where the nucleus is, all right? Now, the Bohr model works very well in terms of explaining the different colors of light emitted by the hydrogen. So basically, according to the Bohr model, what happens is that, okay, at the ground state, the electron is at the lowest orbit, n=1 orbit, and then when you subject it to an electrical discharge, then the electron will gain energy to move to higher orbits. That would be a very unstable situation, so the electrons will fall back to lower orbits. And to explain the different colors of light that is observed, what happens is that if the electron falls from the n=3 to n=2 orbit, then that gives you the red line in the hydrogen spectrum. If the electron falls from n=4 to n=2, that gives you the blue line. And then for the indigo or violet line, that is as a result of an electron falling from n=5 to the n=2 orbit. So that is basically how the Bohr model explains the line spectrum in the hydrogen atom. And in fact, the Bohr model works very well to explain that and other things concerning the structure or the arrangement of the electrons in the hydrogen atom. We're going to look at this equation in a bit more detail, right? We can calculate based on the equation derived by Bohr. We can calculate the energy difference between two orbits when an electron makes a transition from one to the other, right? So this is the equation for the orbit, the final orbit that the electron is moving to. And this would be the formula for the energy of the orbit that the electron is moving from, right? So delta E, in fact, let me see here. Okay, so delta E, let me write this down here because it's not here. Delta E would be equal to E final minus E initial, right? So if you plug in these values or these terms into here and here, you're going to end up with this equation right here, right? Delta E is equal to this minus this. And then what you can do is factor out RH, and you're going to get delta E is equal to minus RH times 1 over N final squared minus 1 over N initial squared. Now, I like to write it this way. I just find it simpler. I would write it like this, equal to minus RH 1 over N2 minus 1 over N1, right? N1 would be the initial orbit from which the electron is leaving, and N2 would be the final orbit. So I'm just using 1 and 2 instead of initial and final, all right? Doesn't matter which one you use, same result will be obtained, all right? So that's a formula that you can use to calculate the energy of a transition from one orbit to another, all right? Now, this is basically showing you some different transitions. And again, this is specifically for the hydrogen atom, right? So as I said before, the Bohr model works well in terms of explaining the colors that we can observe in the line spectrum. And that is basically represented by these transitions here. So just to explain what's happening here, each of these represents the energy levels of the different orbits. This is N equal 1, N equal 2, and so on, right? And as I said before, if the electron is making a transition from N equal 3 to N equal 2, then that will give you the red line. In the case of the transition from N equal 4 to N equal 2, that gives you the blue line. And in terms of the purple line being formed in the spectrum, that results from the transition from N equal 5 to N equal 2, all right? So that's basically how we explain the different colors. And there are some other transitions that we can observe, even though we cannot see them, because the radiation that is produced is outside of the visible part of the spectrum. So we call those transitions from infinity, from 5, from 4, from 3, and from 2, all of them to 1. They will give radiation of a particular type, which we cannot see. And collectively, these are called the Lyman series. The ones that we can see, they're called the Balmer series. And then we have what are known as the Paschen series, which are the ones resulting from the transitions from N equal 5 and N equal 4, both to N equal 3. Again, we cannot, with our eyes, see those transitions, right? The only ones that we can observe in terms of the line that is produced in the spectrum would be these right here, all right? So as I said before, the Bohr model works well in terms of explaining these observations in terms of the type of radiation that is produced when hydrogen is subjected to an electrical discharge. Some definition, well, before we get to the definition, there's one thing I want to mention here, going back to this equation. And in fact, I'm going to get out of this right here, and I'm going to use Word. And let me just get rid of all this that I had from a previous class. And let me get rid of this here. Okay, so what I want to talk about is what could appear to be a bit confusing situation when it comes to the equation I just showed you. So the equation I showed you is delta E. Delta E is equal to minus RH times 1 over N2 squared minus 1 over N1 squared, all right? Now, RH in this case is equal to 2 point, I'm just going to run it off the 3 sig figs, 2.18 times 10 to the minus 19, if I remember correctly. Let me check and make sure. 18, minus 18, my bad. So let me erase this here. So this is 2.18 times 10 to the minus 80. Okay. Now, this formula here, or this part of the formula, delta E, that's a change in energy as you go from one orbit to the other according to the Bohr model. Now, whenever there's a change in energy, radiation would either be absorbed or produced, right? And we can relate that energy change to the frequency of the radiation that is absorbed or produced, according to this equation, which should look familiar to you, right? Delta E is equal to H times nu. Remember, nu is the frequency of the radiation, all right? Now, we also know that c, the speed of light, is equal to lambda times nu, right? So therefore, we can rearrange this to get nu is equal to c divided by lambda. And therefore, this c divided by lambda can replace the nu in this equation. So therefore, the result of that would be that delta E is equal to hc over lambda, all right? So that's the relationship between the energy change or the difference in energy between the orbits where the electron is making the transition from one to the other, and the wavelength of the radiation, which is either absorbed or released. So what I'm going to do now is put this here where delta E is, and the result would be hc over lambda is equal to minus RH times 1 over N2 squared minus 1 over N1 squared, right? And then we can rearrange this to get this expression. 1 over lambda is equal to minus RH divided by HC times 1 over N squared 2 minus 1 over N1 squared. So we have this expression here, right? Now, if you'll notice in this expression, in this part of the expression, we basically have some constants, right? We have RH, which is this right here. We have H, which, if you recall, is equal to 6.63 times 10 to the minus 34 joules second. And we have C, which is the speed of light, which is 3.00 times 10 to the 8 meters per second, right? So what I'm going to do is put these constants here into this part here to see what that gives. So that would be equal to minus 2.18 times 10 to the minus 18 joules divided by H, which is 6.63 times 10 to the minus 34 joules second, times the speed of light, which is 3.00 times 10 to the 8 meters per second, multiplied by 1 over N2 squared minus 1 over N1 squared. So let's see what that collection of constants is going to give. 2.18 times 10 to the minus 18 divided by 6.63 times 10 to the minus 34 times 3 times 10 to the 8. And according to my calculation, when rounded off to 3 sig figs, this part gives, okay, minus 1.10 times 10 to the 7. And in terms of the units, the joules will cancel out, the seconds will cancel out. So the units would be 1 over m, or m to the minus 1. And then the rest would be 1 over N2 squared minus 1 over N1 squared. So basically, 1 over lambda is going to be equal to all of this right here. Okay, now why am I going through all this? The reason why I'm going through all this is because in some textbooks, and I think this is true for your textbook, this is the equation which is given as the Rydberg equation, right? In other textbooks, this is the equation which is given as the Rydberg equation. right? They're both different ways of basically saying the same thing. The only difference between them is that one is expressing the energy difference between two orbits, while the other one is giving an expression which you can use to get lambda, which is the wavelength of the radiation that is either producing or produced in the transition or that causes the transition, right? Furthermore, this RH value here, the constant, we know it to be equal to this right here. But in some textbooks, and again, I think this is true for your textbook, they give you this as the RH value, all right? So I just thought I should basically show you that so that there's no confusion. When I was in school, this is the equation that I learned, right? This is the equation that I'm familiar with. But since I've graduated and so on, I've looked in other textbooks, they use this equation here to represent the RH, or I should say the Rydberg constant. And the RH value in this equation is 2.18 times 10 to the minus 18. But in this equation, it's 1.10 times 10 to the 7, all right? So I just thought that you should be aware of that. Now, this is important because you could use this equation. Let's say you're given a question and you're asked to find the wavelength. Then you could use this equation to find the wavelength. If you're asked to find the energy of the transition, then you would use that equation, the delta E equation, all right? So I just thought you should be aware of that. And in fact, let me see if I can go to the assignment and see what question what we just discussed would apply to. Oh, come on, come on, come on, come on. Okay, so let's see here. Okay, here is, okay, we can do this question now, all right? So this question says, calculate the longest and shortest wavelengths of light emitted by electrons in the hydrogen atom that begin in the n equals 6 state and then falls to states with smaller values of n, all right? So basically, we're assuming that the electron is starting from the n equals 6 orbit, all right? And it's falling to lower orbits, right? So let me just draw a little diagram here just to illustrate what we're talking about here. So we have n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, and then n equals 6. Now, I did not draw this accurately, but let me just say this. As you go further up in terms of the energy of the orbits, the gaps become wider, right? So the gap between n equal 1 and n equal 2 would be like this. And then between n equal 2 and n equal 3 would be like this. And then between 3 and 4 would be like this, and so on and so forth, right? Hold on, let me see something here. Maybe, hold on. Oh, I need to do this first. Let me just check something here. Okay. It's actually the other way around. I misspoke. Right. The energy gap becomes smaller. I don't know what I was thinking. As you can see here. So the n equal 1 and n equal 2 gap is larger. And then n equal 3, n equal 2. So the gaps actually become smaller. Smaller. I misspoke. All right. That's kind of important in order for us to answer this question. So let me go back to the question. Where am I? Let me go here. Let me go here. Okay. So the gap becomes smaller. I misspoke. All right. So what the question is asking for is the shortest and longest wavelength, right? So if the gaps become smaller as you go up, right? What that means is that the smallest gap starting from n equals 6 would be this gap right here. This would be the smallest gap, energy gap, smallest delta E, right? And then the largest would be where we go from n equals 6 to n equals 1. So this would be the largest delta E, all right? But the question is not asking about the smallest or largest delta E. It's asking for the longest and shortest wavelength, right? Now, one of the equations I showed you earlier was this. Delta E is equal to HC over lambda, right? And if you examine this equation carefully, you'll see that there's an inverse relationship between delta E and lambda, right? Basically, the shorter the energy gap, the longer the wavelength, and vice versa. All right? So the question is asking for let's start off with the longest, which would correspond to, the longest wavelength would correspond to the shortest energy gap, right? So we're talking about going from 6 to 5, all right? So to calculate the wavelength going from 6 to 5, that would be given by the formula 1 over lambda is equal to minus 1.10 times 10 to the 7 meters to the minus 1 times 1 over, so the final transition, the final orbit, I should say, would be 5 squared minus 1 over 6 squared. So let me remind you of the formula we're using. We're using 1 over lambda is equal to minus 1.10 times 10 to the 7 meters to the minus 1 over n2 squared minus 1 over n1 squared, all right? This is the formula that we're using, all right? So what we're doing now is calculating for the longest wavelength, right? Lambda. So basically, let's work out what's within the parentheses first. So 5 squared is 25, so do 1 over that, minus 36, 1 over that. And then I multiply by 1.10 times 10 to the 7. So the answer I got, and please check to make sure I'm doing the right thing because I could be wrong. Mode 8. I messed up. Okay. 5 minus 36 times 1.1. Okay, so the answer I got is 1.34 times 10 to the 5, and there's a minus sign here, right? I'm gonna explain how we deal with the minus sign in this case, right? So that's 1 over lambda, which means that lambda is equal to 1 over minus 1.34 times 10 to the 5 meters to the minus 1. So when I do that, the answer I got would be 7.44 times 10 to the minus 6 meters. And that would be a minus sign. Now, let me deal with the negative sign at this juncture. Now, what's the significance of the negative sign? Well, firstly, we should recognize that there's no such thing as a negative wavelength, right? Makes sense, right? You can't have a negative wavelength. Remember, the definition of the wavelength is basically the distance between two successive peaks, right? So there's no such thing as a negative wavelength. So why do we have the negative sign there? Well, the negative sign basically indicates that radiation is being emitted. Energy is being lost as a result of electrons traveling from a higher orbit, higher energy orbit, to a lower energy orbit, from 6 to 5, right? So therefore, because you have a release of energy, that's why we have a negative sign here. So the actual answer is that the wavelength is 7.44 times 10 to the minus 6 meters. And that's it, all right? Well, not quite it, because what we just did is the calculation for the longest wavelength, right? Okay, so what about the shortest wavelength, right? The shortest wavelength corresponds to the largest delta E value, right? So in other words, we're talking going from 6 to 1, right? So we're going to use the same equation here to calculate the shortest wavelength. That will be equal to, well, 1 over lambda would be equal to minus 1.10 times 10 to the 7 meters to the minus 1 times 1 over the final n value, which is 1 squared, minus the initial n value, which is 6 squared. And then we work that out. So let's see what that gives. So that's 1 minus 36. And then I multiply that by 1.1 times 10 to the 7. And the answer I got here, hold on, wait a minute. I keep messing up. 1 minus. Okay, so according to my calculation, this works out to be equal to, wait a minute, I'm sorry. For some reason, this calculator is acting up. Why does it do? Why? Okay, I think I know what I did wrong. I keep pressing the wrong key. All right. 366. So according to my calculation, this works out to be equal to 1.07 times 10 to the 7 meters to the minus 1. So therefore, lambda, and this should be a negative sign as well, lambda is equal to minus 1 over 1.07 times 10 to the 6 meters to the minus 1. So let me do what 1 over that is equal to. So according to my calculation, this works out to be equal to minus 9.35 times 10 to the 8 meters, right? And again, there's no such thing as a negative wavelength, so the actual final answer is going to be 9.35 times 10 to the 8 meters. And this would be the shortest wavelength going from 6 to lower values of n, all right? So that's basically how the law or the equation works, all right? Any questions about this? Any questions? Any questions? No questions? All right, so let's proceed back to the PowerPoint and continue our discussion of, let me get rid of this first. Let me clear this here. Okay, and then let me do this. And okay. All right, so some terms here that I need to talk to you about. I don't know if I mentioned them before. Ground states and excited states. Whenever we talk about the ground state, and this applies to a lot of situations, including what we just discussed in terms of the electron making transitions to different energy levels. The ground state would be the lowest possible energy state. So for example, in the case of the hydrogen atom, where you have the single electron, the ground state would be where the electron is occupying the n equal 1 orbit. Then any other state, we call them the excited state, because those energy states are of a higher energy compared to the ground state, right? So pretty much you have only one ground state and you can have literally an infinite number of excited states, all right? And we can get from the ground state to the excited states by basically finding some way of giving energy to the electron, and the electron will be promoted to the higher energy state. And these are just a couple of ways that that can be done. They can be done by electrical discharge, as we saw in the case of the hydrogen spectrum we saw last time. And then there are some other ways as well, heat and the use of lasers, which will, of course, would contain photons. Then you can have the electrons falling from those higher states to lower states. We call that process relaxation. And when that happens, radiation is produced, as we saw in the example that we just worked, all right? So this is just showing you some examples of transitions that would occur in the hydrogen atom. right? So for example, you can have an electron in the ground state here, n equal 1 state, and then it gains energy, enough energy to be to move into the n equal 5 orbit. And then you can have situations where electrons are in a higher orbit and they fall to lower orbit of energy, such as going from n equal 4 to n equal 2, or n equal 4 to n equal 3, or from n equal 3 to n equal 2, right? In those cases, we have relaxation taking place, and that corresponds to release of radiation of a specific frequency or wavelength, all right? What you'll find is that and we talked about this earlier, what you'll find is that the energy gap is directly, or I should say inversely proportional to the wavelength of the radiation that is either absorbed or produced. So we saw that, and it's based on this equation I gave you earlier. Delta E is equal to HC over lambda, right? Here is delta E, here is lambda, and we can obviously see that's an inverse relationship, right? So as stated here, if the energy gap is high, then that corresponds to shorter wavelengths, such as going from n equal 1 to n equal 5, right? On the other hand, if the energy gap is low or small, then the wavelength for the transition would be longer, right? And that comes directly from the relationship between delta E and lambda. Okay, let me see here. Before we move on, let me just check the assignment here. Okay, I'm going to leave the others for you to do. Based on what we have covered so far, we just did question number 5, right? So you should be able to do number 6, number 7, number 8. Right, okay, good. So you should be able to do those based on what we have covered so far. So what I'm going to do now is move on to de Broglie's equation. Now, and I don't know if there's anybody here who speaks French. If you do, I'll apologize from the outset because I know I just massacred this guy's name. So please forgive me. This guy, he considered all that Bohr and other people have done before. And if you remember, we said that radiation exhibit 2 types of behavior. In one sense, and there are experimental data that bears this out, in one sense, radiation behaves like a waveform. In another sense, radiation behaves like a stream of particles, right? So de Broglie thought about this for a while and did some theoretical work. And he came to the conclusion that if radiation can have both particle and wave behavior, then any moving particle will have wave behavior as well, right? So he did some calculations and theoretical work, and he came up with this equation here, right? The wavelength of a moving object, doesn't matter what the object is, right? It could be something as regular sized as a ball, or it could be an electron. According to de Broglie, he says that lambda is equal to the wavelength associated with the moving particle is equal to Planck's constant, which is h, divided by the mass times the velocity of the object, all right? So that's basically what de Broglie, that's a conclusion that he came to. And this was a very important step in terms of trying to understand the nature of radiation and particles and so on. And it's also very important because this actually formed the basis for the invention and the development of the electron microscope. And simply put, the electron microscope is the most powerful microscope that exists now, right? And it's different from the regular optical microscopes that you probably use in your biology classes, in that instead of using light, right, to bring out the images, they use a stream of electrons, right? And basically the wavelength of the stream of electrons based on the speed can be calculated using this formula. And basically as a result, if I'm not mistaken, the wavelength for a moving electron is smaller compared to the wavelength of a photon. And the result of that is that the images that are brought out by an electron microscope is much better in terms of magnification, all right? And that's as much as I'll say about that. Okay, so that's de Broglie's equation. And then I want to talk about the uncertainty principle, which you won't get too deep into, thankfully. Basically, this is a principle which is put forward by this guy by the name of Werner Heisenberg. And he says that we cannot know at the same time or simultaneously exactly where a tiny particle like an electron is and exactly how it is moving. And the reason for that is that the act of measuring the particle actually interferes with the particle, and therefore, as a result, you cannot tell the position and the speed at which it travels at the same time, all right? And just to illustrate the uncertainty principle, basically, we can use this hypothetical situation here. Now, let's say we have a small particle that's an electron right here, and you have a microscope right here that you're trying to observe the electron with. However, in order for you to see the electron, you need to have a photon of light bouncing off the electron and heading toward the microscope in order for you to see that. But because the photon is hitting the electron will move. So as a result, what you will observe as to where the electron is not where the electron will be at that instant, right? So that's basically the basis for the uncertainty principle. So basically the act of basically measuring where the electron is going to result in electron being displaced from that position, and therefore at that instant, you will not know where the electron is. The best you can say is that the electron was there at a particular time before, but not at the particular instant, all right? Now, why is all this necessary? That's because basically the Bohr model only works for the hydrogen atom and doesn't work for other atoms. And other people have gone into looking into further into how the electrons are arranged. And the conclusion that they came to is that the Bohr model is wrong because of the uncertainty principle. You cannot tell that electrons would be in a defined orbit. So therefore, we have what are another approach that is taken by a guy by the name of Erwin Schrödinger, and this is called quantum mechanics, also known as wave mechanics. Now, let me just say this. Thankfully, you guys don't have to go into details about wave functions and quantum mechanics and so on. And I say thankfully because I had to go through it when I was in grad school. And I'm probably still recovering from that experience. It was not a pleasant experience. It's a whole lot of high-level calculus and partial derivatives. And what I hated most about it was that it was very abstract. Some people love it, but you know, I didn't like it. I just had to do it and try to get the best grade I could get for the course, which, as I recall, was a B+, and it was the hardest B+ I've ever gotten. Anyway, we won't go through all the details of what the wave mechanics is all about. What I'm going to get into is basically the result, right? So according to Schrödinger, we have an equation, which I won't even show you, because if I show you, you'll probably break out in hives or something, I don't know. But that equation basically can be used to calculate what is called a wave function, right? And the wave function is basically a solution to the equation, which I'm not showing you. And it basically represents the energy state of the atom, right? How do we interpret this wave function? Well, the wave function, when squared, gives you the probability of finding an electron in a small volume of space around the atom, right? So basically the wave function, when squared, you can calculate the probability, not exactly where the electrons is located, but the probability of finding electrons within a particular space or volume around the atom, all right? So therefore, as a result, the idea in terms of how the electron behave in an atom is not within orbits, but we call it an electron cloud. That's just basically the region in which you can find a particular atom, right? And we call that region the orbital of an atom. So let me write down the definition of an orbital. So we don't talk about electrons in orbits, we talk about electrons in orbital, right? So an orbital is basically a region in space where the probability of finding an electron is greater than 90%. All right? That's the definition of the orbital, right? And we're going to talk about different shapes of orbitals for different electrons in different energy levels, all right? So basically what we can say here at this juncture is that the Bohr model, even though it explains very well, you know, the properties of hydrogen in terms of the line spectra produced, but it breaks down for other more complex atoms, right? Doesn't work for helium, doesn't work for the other atoms, right? And then furthermore, because of the Heisenberg uncertainty principle, we cannot tell that electrons will be even located within orbit. So therefore, the Schrodinger approach, the wave function approach, is what is used, because it works well, is used to explain the behavior of electrons. So therefore, we cannot talk about electrons lying within orbits. Instead, we say that electrons will be existing in a region of space where the probability of finding it is 90%. Okay, so at this juncture, we're going to talk about what is known as quantum numbers and atomic orbitals. So this is coming again from the Schrodinger approach. The wave functions for the hydrogen atom, and we're going back to the hydrogen atom, but this can apply to other atoms as well, contain 3 parameters that must have specific integral values known as quantum numbers. This comes from the approach, which again, thankfully for you guys, I don't have to show you how these numbers were derived, all right? A wave function with a given set of these 3 numbers is called an atomic orbital. So this is another alternative definition for the atomic orbital, but personally speaking, I prefer the one that I gave you, which, as I said before, is the region in space where the probability of finding an electron is greater than 90%. And as a result of the quantum approach, we can actually calculate the shapes of these orbitals. Again, this is something that I had to do in grad school, which I thoroughly did not enjoy. So let's talk about these quantum numbers, right? The first of which is what is known as a principal quantum number, which is symbolized by the letter n, right? And the values of n are basically positive integers starting from 1 to infinity, right? So basically what we're talking about is the same n values that are used in the Bohr model, right? N equal 1, n equal 2, and so on. We call those the principal quantum numbers, all right? This value of n is related to a couple of things. It's related to the size of the orbital, and it's also related to the electron energy value, right? So it's kind of similar to what n represents in terms of the energy values in the Bohr model. The orbital, in this case, the orbit that is closest to the nucleus will have a lower n value, n equal 1, and then you have n equal 2, and so on and so forth, all right? Orbitals with the same value of n are said to have the same, or said to be in the same principal shell or energy level. We're going to talk more about that shortly. All right, so that's the first quantum number that you need to know about. The second quantum number is known as the angular momentum quantum number, and there's another fancy name for it, the azimuthal quantum number, but I'll leave that alone. And the symbol for that is the letter L, lowercase l, all right? And the values of L starts from 0 and again goes on to infinity. And the key thing that you need to remember about the L values is that it gives some information about the shapes of the orbitals, right? And there's a special letter designation for each value of L. So if L is equal to 0, that corresponds to the S, what we call subshell. For L equal 1, P. For L equal 2, D. For L equal 3, F. And then after that is just alphabetical order. For L equal 4, G, H, I, J, K, etc., right? We're going to tie all of this together shortly. One thing I need to mention here at this juncture is that when it comes to the L value, the possible values of L goes from 0 to n minus 1. Now remember, n is what we talked about before in the previous slide. It is a principal quantum number, right? So basically, the values of L is dependent on the value of L. N represents what we call the shells or the energy levels of the orbits or of the orbitals, while the L value represents what we call the subshells, right? Let me write that word down. So L represents subshells, right? These are the shells, or these are the energy levels that exist within the shells, right? So for example, if n is equal to 2, based on what we said here, remember we said that the possible values of L goes from 0 to n minus 1. If n is equal to 2, then there are only two possible values of L. L can be either 0 or L can be equal to 1, all right? So that's if n equal to 2, L can be equal to 1, which is 2 minus 1, and then the other integer would be 0. Let me give another example. Let me get out of this here. Suppose okay, let me get rid of all this here. All right, so supposing, now remember I said, oops. Remember I said that possible values of L would be all integers from n minus 1 to 0, right? So if L is equal to 2, as we said before, I'm sorry, if n is equal to 2, as we said before, then the possible values of L would be 2 minus 1, which is 1, and then 0, right? If n is equal to 3, then the possible values of L would be 3 minus 1, which would be 2, then 1, then 0, right? If n is equal to 4, then the possible values of L would be 3, which is 4 minus 1, 2, 1, and 0, and so on and so forth, right? So as you can see here, the possible values of L is dependent on what n is. And basically what this means is that, for example, for the second shell, which is n equal 2, there are 2 subshells, right? Because you have 2 values of L. For the third shell, you have 2, 1, 0, so that means that you have 3 subshells, right? For the fourth shell, n equal 4, you have 4 subshells, and so on and so forth, right? So you have the shells, and then within the shells, you have the subshells, and you can determine the number of subshells by determining the number of L values for each n value, all right? Okay, continuing with the PowerPoint here. Okay, so another point being made here is that each of the subshells or each of the orbitals is a different region of space and have different shapes. We'll get into that shortly. All orbitals having the same value of n and same value of L are said to be in the same subshell, which is what I was talking about earlier. Okay, then we get to this quantum number, which is known as the magnetic quantum number, and that is symbolized by the letter ML, right? And this is important because this determines the three-dimensional orientation of the orbital in space. The values of ML is dependent on the values of L according to what is stated here, right? So depending on what the value of L is, the possible values of ML would be going from minus L to plus L. So for example, if L is equal to 2, then the possible values of ML would be minus 2, minus 1, 0, 1, and 2, right? So basically what this tells us is that in the L equal 2 subshell, each of these values represents a particular orbital, right? So there are 5 orbitals in the L equal 2 subshell, all right? Let me give another example. Let me go back to this right here. And let me get rid of this right here. So when it comes to the L values, as I said before, I'm sorry, not the L values, the ML values. ML values would be equal to all integers from plus L through 0 through to minus L, all right? So as we said before, if L is equal to 2, the possible values of ML would be plus 2, plus 1, 0, minus 1, minus 2, all right? So that's if L is equal to 2. If L is equal to 3, then what would be the possible values of ML? -3, -2, -1, 0, +1, +2, +3, right? And if L is equal to 1, what are the possible values of ML? If L is equal, I'm sorry? -1, 0, +1. Exactly, right? So that's how you get ML value. Each of these ML values represents an orbital, right? So you can tell, based on the L value for the subshell, how many orbitals are within that subshell, right? That's why we need to know how to calculate that, and this is how we do that, all right? Okay, going back to the PowerPoint. Oh, wait a minute. Okay, so to summarize what we have just talked about, this is the result. N can have values from 1 to infinity. This is just dealing with the first 3 shells, right? If N is equal to 1, then the only possible value of L will be 0, and therefore the only possible value of the ML value will be 0. So therefore, as far as the subshell is concerned, we designated 1S. Remember the SPDF notation that we talked about. S is where L is equal to 0. So that's why we have S here. The 1 here comes from the principal quantum number, right? And the number of orbitals present would simply be 1 because there's only 1 ML value. And then when we get to the second shell, we have N equal 2, but L can have a value of 1 or 0. If L is equal to 0, ML is equal to 0, the designation would be 2S, right? S because L is equal to 0, and 2 here because the principal quantum number is 2, and there's only 1 orbital in the N equal 2 subshell. I'm sorry, into the 2S subshell. But of course, we can have L equal 1, right? When L is equal to 1, there are 3 possible values of ML, -1, 0, +1. Each of them represents a 2p orbital. P because L is equal to 1, I'm sorry. So therefore, there are 3 2p orbitals in the 2p sublevel, all right? And then so on and so forth for the 3rd, 4th, 5th shell, right? So that's basically how you can determine, well, a couple of things. The type of orbitals, the number of orbitals in a particular subshell, how many subshells are present in a particular shell, and so on and so forth, all right? So therefore, that's how we derive all these different values in terms of the different quantum numbers and the different types of shells. Okay, so what do these orbitals look like? Well, if you were to plot the probability versus distance, and I think this is for the 1s orbital, basically this is the shape that you're going to get, all right? But if you do this plot, now, kind of hard for me to explain what this is, but basically what you're doing in this plot here is that you're finding the probability within a certain region or a certain volume around the atom, right? For a particular electron, the probability. And this is what you're going to get here, right? This is basically describing a spherical relationship for an s orbital, which looks like this right here, right? So this is basically the shape of the s orbital, more specifically the 1s orbital. And this is basically showing you, basically, it's kind of like taking many pictures of the electron while it's moving, and you overlay them over each other, and you get this distribution right here. So that's basically the shape of the 1s orbital. In the case of the 2s orbital, it's a similar shape, but there's one difference when compared to the 1s orbital. In the case of the 2s orbital, you have a region right here, which is called the node. And in that region, the probability of finding the electron there is 0, all right? So that's what happens in the case of the 2s orbital. And then if you were to look at the 3s orbital, there will be 2 nodes. In the case of the 4s orbital, there will be 3 nodes, and so on, all right? So that's basically what the shape of the s orbitals look like. As far as the p orbitals are concerned, this is what they look like, all right? This is what they look like separately, and this is what they look like together. Remember, the p orbitals, they occur in sets of 3s. Whenever you have a p orbital within a particular seat, whenever you have a, I should say, let me rephrase that. Whenever you have a p sublevel, there will always be 3 p orbitals, right? And this is how they are arranged separately. You have 1 p orbital aligned along the x-axis here, of the three-dimensional Cartesian system, XYZ system. You have another p orbital aligned here along the y-axis, and then the third one will align along the z-axis, right? So basically the p orbitals are at mutual right angles, and this is what they look like together. And then when it comes to the d orbitals, I won't even expect you to memorize what these look like, but you need to know that they exist, and you need to know that there are 5 of them, right? So wherever you have any d subshells, there'll be 5 d orbitals, all right? And then you have the f orbitals, which looks even more complicated, and there are 7 of them, right? So there's only 1 s orbital that can exist within any subshell. There are only 3 p orbitals that can exist within any p subshell, 5 d orbitals within any d subshell, and 7 f orbitals in any particular f subshells, all right? So that's basically, those are the numbers that you need to remember when it comes to the subshells. Okay, one last one last quantum number that you need to know about, and that is called the electron spin quantum number, which is symbolized by ms. And this one is the least complicated of all because ms can only have 2 values, 2 possible values. And it's actually related to the fact that whenever you have an electron spinning, it generates a magnetic field, right? I don't know how many of you have done physics, but in physics, there's a thing called the right-hand rule, which talks about the fact that if you have a negative charge spinning in a direction, you can predict the direction of the magnetic field that's generated using your right hand, right? So if the electron is spinning according to the direction of your fingers like this, then the magnetic field generated would be in the direction of your thumb, right? So that's a right-hand rule. So that's why with this electron spinning in this direction, the magnetic field going from north to south would go in that direction, right? And then you have, when the electron is spinning in the opposite direction, the magnetic field will be pointing in the other direction going down. So for an electron in any atom, those are the only 2 possible spin states, right? And they're symbolized by the ms values. There are only 2 possible values as a result. One is +½ and the other one is -½ all right? And that's it as far as electron spin is concerned. Those numbers are not dependent on the other quantum numbers that we talked about earlier, all right? And this is, I won't go into this, but the spin quantum numbers were actually discovered as a result of this experiment. I won't even go into that. I leave that for you to read upon, all right? Okay, so that represents the end of this chapter right here. And I want to go back to the assignment because there's one particular question. Oh, let's look at this question here first before we move on to the other one I was thinking of. So this question says, what is the velocity of a neutron which exhibits a wavelength, and it gives the mass of the neutron, which exhibits a wavelength of 580 nanometers. Now, the equation that you're going to use for this, let me do this here, is the de Broglie equation. Again, let me apologize for massacring that guy's name. But the de Broglie equation is lambda is equal to h over mv, right? Now, let me remind you, h is Planck's constant. Planck's constant. Lambda is the wavelength. M is the mass in kilograms. Mass in kilograms. And v is the velocity in meters per second, right? So that's the equation that you're going to use to answer question number 9A and also 9B. But I'm just going to do 9A, and based on that, you should be able to do 9B. All right, so what the question is asking for is this, the velocity, right? So based on that equation, we can say that the velocity is equal to h over m times lambda. And all we have to do is put the numbers in. So h is 6.63 times 10 to the minus 34 joules second, divided by mass, which is given here, but it's given in grams. So we have to convert that to kilograms. So that means we have to multiply by 1 kilogram divided by 1,000 grams here. And then we multiply that by the wavelength. Now the wavelength here is given in nanometers. What we have to do is convert that to meters. So 580 nanometers. Nano means 10 to the minus 9. So 1 nanometer down here, 10 to the minus 9 meters up there. And that's basically how that is done. So let's see here. 6.63 times 10 to the minus 34 divided by 1.67 times 10 to the minus 24 divided by 1,000 times 580 times 10 to the minus 9. And according to my calculations, this works out to be equal to 0. Let me do this again. I keep messing up on these things. 6.63 times 4 divided by 1.67. 580. Okay, I'm confident of this answer, which is 0.68. And what are the units? The units will be meters per second. And the reason why that's the case is because the joule unit, let me just take this out here. The joule unit is the same thing as kilograms meter squared over second squared multiplied by second, right? So basically the kilogram units will cancel out here and here. Gram units will cancel out here and here. Nanometers cancel out. This meter will cancel out with one of these 2 meters squared. This second will cancel out one of those 2 seconds squared. So the final units will be meter second, all right? And that's how that is done. Any questions about that? Any questions? Any questions? Any questions? All right. Oh, what did I do that for? Sorry about that. Why did I do that? Okay. Let me scroll down. So if you understood what I just did, you should be able to do the B part. All right. So I'm going to leave you to do that part. Let me scroll down to, okay, so this is what I want to get to. So this is based on what we just discussed with respect to the quantum numbers and the rules, right? So let me just remind you of the rules. Let me just put a little notation somewhere here. Let me do it over here. So remember I said that the values of n can go from 1, 2, 3, all the way to infinity, right? The values of L would be equal to plus, would be equal to, I'm sorry, n minus 1 and all integers through to 0, right? The values of ML can go from plus L through 0 and all integers to minus L, right? And then MS can only have one of 2 values, plus half or minus half, all right? So those are basically the rules that we need to abide by in order to answer these questions that is being asked here. So the question that's being asked here is, which of the following are possible for an electron in an atom? For the sets of quantum numbers that are not possible, state what is wrong with each set, right? So this is based on what we have discussed right here, right? So in the case of A, it says n is equal to 1, L is equal to 0, ML is equal to 1, and MS is equal to plus half. Is that possible or impossible based on these rules right here? N is equal to 1, L is equal to 0, ML is equal to 1, and MS is equal to plus half. Is that possible or impossible? Impossible. Why? I'm sorry? Right, because if L is equal to 0, ML cannot be equal to 1. The only possible value for ML would be 0, right? So basically, the answer here would be impossible because if L is equal to 0, ML can only be 0. All right? So that's the answer to that one. All right? Okay, what about B? N is equal to 9, L is equal to 7, ML is equal to -6, and MS is equal to -half. Is that possible or impossible? Why do you say that? Hmm? Yeah, if N is equal to 9, look at this rule right here. If N is equal to 9, right, then L can be equal to 9, 8, 7, 6, 5, 4, 3, 2, all the way to 0, right? So L can be equal to 7 if N is equal to 9, right? And as far as ML is concerned, if L is equal to 7, then the possible values of ML can go from 7, right, to -7. So 7, 6, 5, 4, 3, 2, 1, 0, then -1, -2, -3 to -7. So ML can be equal to -6. And remember, MS can only have one of two values, plus or -half. So this is possible. There's nothing wrong with this set of numbers, all right? Okay, let me scroll down. Hold on, let me do this here. In fact, let me get rid of what we have there. Hold on. All right, hold on. Okay, so let me scroll down to here, and then let me get rid of what I just wrote. Okay, in fact, hold on. Okay, I'm trying to figure out how to get rid of this part without. Oh, okay, erase, of course. Okay, C. Says N equal 2, L equal 1, ML is equal to 0, and MS is equal to 0. Is that possible or impossible? Impossible, because? Exactly. So the answer here would be impossible, because MS can only be either plus or -half, right? So MS cannot be 0. Okay, what about D? N is equal to 1, L is equal to 1, ML is equal to 1, and MS is equal to +half. Is that possible or impossible? Why do you say it's possible? Let's start with N equal 1, right? Well, let's start with L equal 1. If N is equal to 1, remember what we say here. What would be the possible values of L if N is equal to 1? 0. There's only one possible value of L, that would be 0. So therefore, this would be impossible. Because if N is equal to 1, L can only be 0. And that's it. All right? Okay, let me erase this here. I think there might be one more further down. Okay, that's the last one. Okay. So it says here N equals 3, L is equal to 2, ML is equal to -3, and MS is equal to -half. So is that possible or impossible? N is equal to 3, L is equal to 2, ML is equal to -3, and MS is equal to -half. Is that possible or impossible? Okay, impossible. Why? Because? Right. Right. So impossible because oops. Because if what was it now? If L is equal to 2, ML cannot be minus 3. All right? And that's basically how that is done. All right, so that's basically it for this chapter. Any questions about any of these? Any questions? Any questions? No? All right, so basically, make sure you complete the rest of this. Let me go to, so that's assignment number 7. Let me set up a Dropbox for this. Okay, when shall I make this due? Today is what? Today is the 31st. Okay, I'm going to make this due Friday. All right. Of course, if you have any questions, feel free to contact me. I'll be available for office hours on Thursday here in my office. I don't remember the hours. I think it's 8 to 11 and then 2 to 5. And then Friday, I'll be available online. And I think I'm going to make myself available in person at the Ocala campus on Friday. I'm not sure yet. From 2 to 5. So those are the times I'll be available. So if you have any questions concerning this assignment. Oh, another thing too I need to mention. As far as the test is concerned, I haven't picked them up yet. So, well, no, I'm sorry. I'm confusing you guys with the online class. I've graded a couple of them. But there are a couple of you who have missed the test. So make sure that you make arrangements with me to make it up so that you can get that out of the way, all right? I should be able to grade those tests finally before this week is out, so you'll see your results. What's up? Oh, thank you. Thank you very much. Not with me, I'm sorry.
That's okay. I can fit one.
Yeah, it's there online, yeah.